Have you ever wondered how digital circuits function? As the underpinning technology of our modern world, digital circuits perform a multitude of tasks, from simple functions like turning on a light to complex operations like running a computer. At the heart of these circuits lie two fundamental components: Mealy and Moore machines. You see, digital circuits don't just occur naturally. They're the product of intricate design processes that hinge on the principles of finite state machines. Finite state machines are a class of models in computer science and engineering that can exist in a finite number of states. They respond to inputs, transitioning from one state to another, and producing outputs based on their current state. Enter Mealy and Moore machines. These are two types of finite state machines that form the bedrock of sequential circuit design. They differ in how they determine their outputs and when these outputs change, but both are crucial tools in the digital design toolkit. Mealy machines are dynamic. Their outputs are dependent on both the current state and the inputs. This means that output changes can occur asynchronously with input changes, providing a certain level of flexibility. On the other hand, Moore machines are steady. Their outputs depend solely on the current state. This results in synchronous output changes, offering a level of predictability and synchronization. These principles aren't just theoretical constructs. They're represented in digital design textbooks, serving as a guide for designers and engineers. A notable example is David M. Wakerly's Digital Design, Principles and Practices, a respected resource in the field of digital design. However, understanding these machines isn't just about knowing their definitions. It's about understanding the role they play in designing sequential circuits, how they interact with inputs and states, and how they produce outputs. It's about appreciating the intricacies of their design, the considerations that go into their implementation, and the impact they have on our digital world. Now that we've set the stage, let's delve deeper into Mealy and Moore machines. As we journey through the fascinating world of digital circuits and finite state machines, we'll discover the unique features, strengths, and challenges of these two fundamental components. So buckle up and let's get started. First, we'll explore Mealy machines. Mealy machines are a type of finite state machine named after George H. Mealy, who introduced them in the mid-20th century. They're a fundamental concept in digital design, used widely to design sequential circuits. In Mealy machines, the outputs are dependent on both the current state and the inputs. This means the output can change as soon as the input changes, even without waiting for a clock pulse. This is referred to as asynchronous behavior. So what's an output function? In a Mealy machine, the output function is a combination of the current state and the inputs. This means that the output may change during a clock transition, making the design of Mealy machines a bit more complex. Now let's talk about state transitions. In Mealy machines, transitions between states are triggered by clock pulses or external events. The next state is determined by both the current state and the inputs. Let's illustrate this with a simple Mealy machine state diagram. Picture two states, S0 and S1. The transition from S0 to S1 happens when the input is 1 and the output is 0. The transition back from S1 to S0 happens when the input is 0 and the output is 1. So, in this example, the outputs are associated with the transitions between states. You'll often find Mealy machines in systems where the output is expected to react rapidly to changes in the input. However, their asynchronous nature may introduce timing hazards, which is something to consider when choosing between Mealy and Moore machines for your design. That sums up the basics of Mealy machines. Now let's turn our attention to Moore machines. Now let's examine Moore machines. Moore machines are a type of finite state machine used in digital design. What sets them apart is that their outputs are solely dependent on the current state. This means that changes in output occur synchronously, in step with state transitions. There's no need to wait for an input change. When the state changes, so does the output. The output function of a Moore machine is a direct function of the current state. It doesn't consider inputs. This simplification makes Moore machines easier to understand and design. State transitions in Moore machines, similar to Mealy machines, are triggered by clock pulses or external events. However, the next state in a Moore machine is determined only by the current state and the inputs. There's no need to consider the current output. Let's look at a simple Moore machine state diagram to illustrate these concepts. Imagine two states, S0 and S1. The machine transitions between these states based on inputs. The output is associated with the current state, not the transition. If we're in state S0, the output is 0. If we're in state S1, the output is 1. This example clearly illustrates the characteristics of Moore machines. The output is determined solely by the current state. Changes in output occur synchronously with state transitions, and the next state is a function of the current state and inputs. Moore machines offer several advantages, including predictable and synchronized output, and a simpler design process, as the output logic is decoupled from state transitions. However, they may require more states than Mealy machines to achieve the same functionality, leading to larger state diagrams. But remember, there's no absolute better between Mealy and Moore machines. The choice depends on the specific requirements of your digital design task. With that, we've covered the fundamentals of Moore machines. Now let's compare and contrast Mealy and Moore machines. It's time to compare and contrast Mealy and Moore machines. To start, let's look at output timing. In a Mealy machine, outputs can change asynchronously with input changes. This means that the output can change at any time, not just during a clock transition. On the other hand, in a Moore machine, outputs change only during state transitions, synchronously with the clock. So, the output will only change when the state changes. Next, consider the number of states. Moore machines may require more states than Mealy machines to achieve the same functionality. This means that a Moore machine may be larger and more complex. Conversely, Mealy machines can have more compact state diagrams, which can make them easier to work with in certain situations. Thirdly, let's discuss output signal complexity. Moore machines simplify the design by decoupling output logic from state transitions. This can make the design easier to understand and manage. However, Mealy machines may provide more flexibility in defining output logic, which can be beneficial for certain applications. Lastly, we have timing and synchronization. Mealy machines may introduce timing hazards due to asynchronous output changes. This means that a Mealy machine may produce unexpected results if inputs change rapidly. Moore machines, on the other hand, offer a more predictable and synchronized output, which can be beneficial in applications where timing is critical. In conclusion, the choice between a Mealy and a Moore machine depends largely on the application. If synchronous and predictable output timing is crucial, a Moore machine may be preferred. On the other hand, if the application requires a compact design with flexible output logic, a Mealy machine may be a better choice. That's a look at some of the main differences between Mealy and Moore machines. Let's wrap up by considering some design considerations. Output. When designing digital circuits, there are several key considerations to keep in mind. Firstly, think about application requirements. The choice between Mealy and Moore machines should be based on the specific needs of your project. If the timing of your output is crucial and needs to be synchronous and predictable, Moore machines might be the better choice. On the other hand, if you require more flexibility in defining output logic and a more compact state diagram, a Mealy machine could be the way to go. Next, consider the state diagrams. These are a visual representation of the system behavior. They give a clear picture of state transitions, input conditions, and output values. When designing your state diagrams, remember that in the case of Mealy machines, the outputs are associated with the transitions between states. For Moore machines, on the other hand, the outputs are associated with the states themselves. Finally, never underestimate the importance of testing and verification. After designing your digital circuit, you need to verify its correctness through simulation and testing. This stage is crucial for detecting any flaws or potential improvements in your design. Particularly, pay close attention to the impact of output timing on the overall system. Remember, in Mealy machines, outputs can change asynchronously with input changes, which may introduce timing hazards. On the contrary, Moore machines offer a more predictable and synchronized output, changing only during state transitions. In conclusion, the choice between Mealy and Moore machines depends on multiple factors, including the specific requirements of your application, the complexity of your state diagram, and the importance of output timing and synchronization. Both types of machines have their strengths and weaknesses, and understanding these is key to making the right choice for your digital circuit design. And that's a wrap! We hope this video has given you a deeper understanding of Mealy and Moore machines and their role in digital circuit design. Thank you for watching.